Hello dear students, let us discuss about inner product and inner product spaces. So this is our second module, chapter 2, Hilbert spaces. And let capital H be a linear space over C, where C is the set of all complex values with a complex valued function of two variables, inner product of x comma y, where x and y belongs to capital H. Then the function inner product of x comma y is a function from capital H cross H to C, with the satisfying three properties. First one is linearity with respect to the first argument, which means inner product of ax1 plus bx2 comma y is equal to in a into inner product of x1 comma y plus b into inner product of x2 comma y, which simply means inner product of x1 plus x2 comma y can be written as inner product of x1 comma y plus inner product of x2 comma y. Similarly, inner product of a x1 comma y can be written as a into inner product of x comma y. This is linearity with respect to the first argument. The second one is inner product of xy conjugate is equal to inner product of yx. That is, the inner products, the arguments can be interchanged. Third one means it is non-negativeness. That is, inner product of xx greater than or equal to 0 and equal to 0 only if and only if x equal to 0. If a function satisfying this three conditions is known as an inner product, and it is also known as a scalar product, inner product or scalar product. Now see semi-linearity of inner product with respect to the second argument, which means inner product of x comma ay1 plus by2 is equal to a conjugate into inner product of xy1 plus b conjugate into inner product of xy2, which simply means inner product of x comma or x1 comma a into y1 can be written as inner a conjugate into inner product of x comma y1. And if it is of the form ax1 comma y1, which means a into inner product of x1 y1, if we are taking the scalar from second argument, if it comes outside of the form a conjugate, if it comes from first argument, it is a. That is, it is the function, it is the value itself. Otherwise, if it comes from the second argument, we will count its conjugate. Now, we can prove the semi-linearity as follows. That is, inner product of x comma ay1 plus by2 can be written as inner product of ay1 plus by2 comma x conjugate by the property, by the second property, and this is equal to a into inner product of y1x plus b into inner product of y2x, the whole conjugate, by the linearity with respect to the first argument. Then, which is equal to a inner product of y1x whole conjugate plus b into inner product of y2x whole conjugate, again by linear the first variable, and this can be written as a conjugate into xy1 plus b conjugate into xy2, and this is known as the semi-linearity of inner product with respect to the second argument. Now these are some example for inner product spaces. First one is with a capital H is equal to Cn, where C is the set of all complex values. We are taking two values from Cn, x comma y, of the form x is equal to a1, a2, etc. an, and y is equal to b1, b2, etc. bn. And if we are defining inner product of x comma y as sigma 1 to n ai bi conjugate, it will be an inner product. And here gives an example to show how to find an inner product in Cn. So for example, we are taking C2 as our linear space, and we are taking two pair, that is x is equal to 1 plus I comma 1 minus I and y is equal to I comma 2I belongs to C2. And here we are finding inner product of xy by using the formula, that is inner product of 1 2 and AI bi conjugate. That is here inner product of x comma y is equal to inner product of 1 plus I comma 1 minus I comma I comma 2I. For example, we are taking such values, and by definition it is 1 plus I into I conjugate plus 1 minus I into 2I conjugate. By simplifying, and we know that I conjugate is modulus of I square, and modulus of I square is minus 1, modulus of I square is 1. All such things we can find its inter product. And now let us think how to show that is an inner product. That is how to show that the values, if we are finding two values x y belongs to Cn, we can prove that it is inner product. That is, here we are taking three values to prove the three conditions required for the inner product. That is, x is equal to a1 a2 etc. n belongs to Cn, y is equal to b1 b2 etc. bn belongs to Cn, and z is equal to c1 c2 etc. cn belongs to Cn. And inner product of x comma y can be written like this: a1 b1 conjugate plus a2 b2 conjugate plus etc. a and bn conjugate. First we had to prove the linearity, this first argument corresponding to the first argument. So we are starting from this. That is, first one, inner product of kx plus ly comma z. As we have already ABC, we are taking the constants as k comma l. So this is equal to inner product of ka1 etc. kan plus in lb1 etc. lbn comma it's a triplet c1 c2 etc. cn. Then we know that the properties of this n tuple, not triplet, sorry, n tuple, we know that this is ka1 plus lb1 comma etc. kan plus lbn comma c1 c2 etc. Then by property of this inner product, we can write like this: ka1 plus lb1 c1 conjugate plus etc. kan plus lbn cn conjugate. And by simplifying, we will get k inner product of x comma z plus L into inner product of yz. Thus we proved the linearity corresponding to the first variable, that is the first property required to be an inner product. Now let us go to the second property, that is starting with inner product of xy conjugate, which is equal to inner product of first coordinate is a1 a2 etc. an and second coordinate is b1 b2 etc. bn, this whole conjugate. Then the next line we found the inner product value, that is a1 b1 conjugate plus a2 b2 conjugate plus etc. a and bn conjugate. But we started with x inner product of xy whole conjugate, therefore the summation whole conjugate, which means a1 conjugate b1, since we know that b conjugate is equal to b. So this is inner product of yx. So we proved the second property also. Third one, inner product of xx is equal to a1 conjugate plus etc. an conjugate. We know that z bar is modulus of z square. So here a1 conjugate means modulus of a1 square plus etc. That is sum of positive terms, since each term is a square. So sum of positive terms means inner product of xx is greater than or equal to 0. Let xx equal to 0, which means sum of positive terms is equal to 0. Thus each term should be 0, that is each ai is equal to 0, that is x equal to 0. Hence we proved that if we are defining inner product in Cn of the form sigma ai bi conjugate, we can simply prove that it is an inner product, that is it satisfies the three conditions required for an inner product. Okay, now so it's an inner product. So we'll say this is our first example. Second example is L2 space, little L2 space. So in little L2 and one element in little L2 means it is of the form a1 a2 etc. It's an infinite sequence. Then we are taking two values x and y, and we can define the product in L2 of the form inner product of xy is equal to sigma 1 to infinity ai bi conjugate, that is a1 b1 conjugate plus a2 b2 conjugate plus etc. Similarly, as we proved for Cn, we can prove that this L2 is an inner product space with inner product like this of the form inner product of xy is equal to sigma ai bi conjugate. Now by Holder's inequality we know that modulus of inner product ai bi conjugate is less than or equal to sigma modulus of ai square whole raised to 1 by 2 into sigma modulus of bi square whole raised to 1 by 2. And since these two terms belongs to L2, the product should be less than infinity. That is, this modulus of sigma ai bi conjugate is finite, which means we can define a function of the form inner product of xy is equal to sigma 1 to infinity ai bi conjugate. That means the definition makes sense. That is, it is defined. It's a well defined on L2 cross L2. Now also we have a inequality of the form modulus of inner product of xy less than or equal to norm x into norm y. So to prove that, let us start with modulus of inner product of xy, and by definition it is modulus of a1 b1 conjugate plus a2 b2 conjugate plus etc. That is, it is modulus of sigma ai bi conjugate, which is less than or equal to sigma modulus of ai bi conjugate, since we know that modulus of x plus y plus etc. or z something like that, which is less than or equal to mod x plus mod y, and this can be extended. Hence we can write modulus of sigma ai bi conjugate is less than or equal to sigma modulus of ai bi conjugate. By Holder's inequality we know that sigma modulus of ai square whole raised to 1 by 2 into sigma bi conjugate square whole raised to 1 by 2. But sigma modulus of bi conjugate is nothing but modulus of bi. Therefore, by Holder's inequality we can prove that modulus of sigma xy is less than or equal to norm x into norm y. With here we are p is equal to 2 and q is equal to 2. Here we are considering p and q as 2. Now this is our third example is C2 of closed interval AB, and these are functions, continuous functions. It is two integrable functions. We can write like this: integral of, we are defining inner product of fg as of the form inner product of f comma g is equal to integral a to b f of t g of t conjugate dt. And we have a Cauchy-Schwartz inequality in the case of integrals, that is modulus of integral f comma g is less than or equal to norm 2 of f into norm 2 of g. To prove this, again we are starting with modulus of inner product of f comma g. We apply the formula that is inner product a to b f of t g of t conjugate dt. As we know that modulus of integral f of t dt is less than or equal to integral of modulus f of t dt. We can write like this again, which is less than or equal to integral a to b modulus of f of t whole square dt whole raised to 1 by 2 into integral a to b modulus of g of t conjugate square whole raised to dt whole raised to 1 by 2, and modulus of g of t conjugate is same as modulus of g of t, and here we used Holder's inequality with the p equal to q equal to 2, and hence it is less than or equal to norm 2 of f into norm 2 of g. Now let us prove the Cauchy-Schwartz inequality. And so the first theorem is Cauchy-Schwartz inequality, that is, as we have seen before, modulus of inner product of x comma y is less than or equal to inner product of x comma x whole raised to half into inner product of y comma y whole raised to half. So for the proof we are letting a function p of x as inner product of x raised to 1 by 2, and we know that inner product of any two value, inner product of x is greater than or equal to 0. So we start with like this: 0 less than or equal to inner product of x minus lambda y comma x minus lambda y. And the next step we simplify it by the linearity property. which is less than or equal to inner product of xx into from this term. We can take lambda is in the position of second argument. If we are taking that lambda outside, we have to take outside as conjugate of lambda, that is lambda conjugate into inner product of xy. Next term is inner product of lambda y comma x. Again, lambda is in the first position of first argument. So if we are taking lambda from that, it can be right like this: lambda into inner product of yx plus lambda, and if we are considering the third term, then it is of the form inner product of lambda y, that is lambda as in both the place of first and second argument. That is, if you are taking from the first argument, it will be lambda. If you are taking from the second argument, it will be as lambda conjugate, that is lambda conjugate inner product of y. Lambda conjugate means, or lambda bar means z bar form, that is modulus of z square, that is modulus of lambda square. So this is of the form inner product of xx minus lambda conjugate inner product of xy minus lambda inner product of yx, which can be written like this: inner product of xx minus lambda inner product of yx whole conjugate minus lambda into inner product of yx. We know that z plus z bar by 2 is equal to real part of z, where z equal to x plus iy. Z equal to x plus iy means z conjugate is equal to x minus iy, which means z plus z bar is equal to x plus iy plus x minus iy, that is 2x, that is 2 into real part of z. Similarly, here we have minus of lambda into inner product of yx conjugate of the form z bar plus lambda into inner product of yx. This is of the form z plus z bar, which can be written as 2 into real part of lambda into inner product of yx. Okay. So plus modulus of lambda square into p of y, the whole square, we are marking it as 2. And throughout the theorem, we are assuming that inner product of x comma y is not equal to 0. So we can take lambda is equal to p of x the whole square divided by inner product of yx. We are taking as this for the proof. Again, by substituting this value from in equation 2, we will get 0 less than or equal to p of x the whole square minus 2 real part of p of x the whole square by inner product of yx into yx plus p of x the whole raised to 4 divided by modulus of inner product y comma x the whole square p of y whole square. And simplifying, we will get of the form 0 less than or equal to minus p of x whole square plus p of x raised to 4 divided by modulus of inner product y comma x the whole square p of y whole square. So p of x the whole square is inner product of x comma x whole raised to half inner product of px whole square is equal to inner product of x comma x, and we have already assumed that inner product of xy is not equal to 0, which means inner product of xx is not equal to 0. So we can divide throughout with, or we can cancel p of x square on both sides. That is, we are dividing both sides by p of x the whole square. Hence we will get 0 less than or equal to minus 1 plus p of x the whole square divided by modulus of inner product y x the whole square p of y whole square, which is same as modulus of inner product yx is less than or equal to p of x into p of y. And since modulus of z is equal to modulus of z conjugate, we can write like this: modulus of inner product of yx is same as modulus of inner product of xy. Hence we have the result. Now the equality holds if and only if x equal to lambda y. We can easily prove that x given x equal to lambda y by substituting here. We can prove that this is equal to p of x into p of y. Hence proof.